So is my screen visible?
Yes, sir.
Okay. So we were discussing in the previous class. I was just giving you a brief introduction about the gas turbines, then some of their applications, and then we were looking at the history of jet engines, which also use gas turbines, because jet engines also are one of the most important component of our course. So we were discussing about how the jet engines were developed and what were the military aircraft engines before that, and we had discussed how parallelly two designs were developed, one in Germany by von Owen and one in UK by Frank Whittle. So before moving on to the next part, what I will do is I will quickly uh, just give you a brief idea about the different types of jet engines that are used at present, okay, or may be used in future. And we will actually revisit this slide later on when we go through the individual topics. Like later on, we will go through turbojet, turbofan, so similar types of engine one by one. So at that time, we will revisit these slides again. So why I want to go through them now is to give you a feel of how actually the different types of engines look like and how they work, so that when you read about the cycles and thermodynamics, you can relate them to the actual like the actual physical engine, jet engine. Okay, different types of jet engines. So the first type of jet engine which were developed, these were developed like right after the World War II, were turbojet engines. Okay, so these are the so you can say the most basic type of jet engine in principle. So let us take a look at how this turbojet engine works. So what we have is a duct, you can say, and at the front of the duct we have a set of compressors. Then there is a combustion chamber, and then there are multiple stages of turbine. Okay, we know that the three main components of a gas turbine are compressor, combustion chamber, and turbine. And if you consider jet engines, there are two additional important components. One is the nozzle and one is the diffuser in the front. So here the diffuser is not shown properly. There will be actually a diffuser in front. Diffuser is the opposite of a nozzle. So what happens is that the incoming air comes at a high velocity because the engine is moving at a high velocity. So relative to the engine, the incoming air comes at a very high velocity, and we do not want to waste that energy that is present in the incoming air. Okay, that kinetic energy. So the diffuser slows down the flow and converts the kinetic energy to enthalpy. So it increases the pressure and temperature of the fluid. Main idea is to increase the pressure of the fluid so that less amount of compression is needed in the compressor. Some compression is done by the diffuser itself. Okay. So this is done by, if it is a subsonic flow, you need a increasing cross-sectional area, like the opposite of a nozzle. If it is a supersonic flow, you need a decreasing cross-sectional area. Okay. So depending on so typically if the aircraft is subsonic aircraft, you will have a diffuser which has a slightly increasing cross-sectional area. Let me show you one photograph so that you can see how it looks like, but it is not very clear. So actually this region in front of the fan, this is a turbofan engine, but this portion that you see in front of the fan is not just arbitrarily designed. This is actually a diffuser with an increasing cross-sectional area. Any of the aircraft that you board nowadays are turbofan aircraft. Any of the large aircraft that you board are turbofan aircraft. So the front section, if you see carefully, you will see the section like this. Then you can see the fan, and inside you will be able to see other like core engine area. But the front section is the diffuser where the air is slowed down. So after the air gets slowed down, it is compressed by the compressor. The multiple stages of compressors are required. Each stage can only compress up to say 1.5 times. So the typical compression ratio nowadays for modern aircraft is maybe it is around 20 or even larger. Okay. So the increase in pressure ratio. Then fuel is injected. So multiple combustion chambers are there arranged around the central shaft, and the fuel is injected in each of the combustion chamber, and combustion process. So the high pressure, high temperature air which comes in moves out at even higher temperature. Combustion occurs at constant pressure because the combustion chambers are open at both ends. Unlike IC engines, in this case, well, in IC engines there is a piston which is constricting the movement. So the pressure builds up. Here the pressure does not build up. So it occurs, combustion occurs at constant pressure, and the hot combustion products, which are water vapor and carbon dioxide. So for gas turbines, typically combustion is very good, means the amount of combustion. So almost 99% of the energy that is in the fuel is released as useful energy. Okay, the fuel almost gets fully combusted because of the very low fuel air ratio that is used, or very high air fuel ratio. Means the amount of air used is very high. You have a very lean mixture, so most of the fuel gas, almost the entire fuel gas burned up. By the way, what is the reason of using very high air fuel ratio? Anyway, we'll discuss this later, but I'm just curious whether you know or not. Why very large amount of air is used?
Sir, turbine cooling.
Not directly turbine cooling. Means how turbine cooling?
Temperature.
Sorry?
To control the temperature in the combustion chamber.
Yes. So to reduce the temperature, if you have more air, it will reduce the peak temperature in the combustion chamber, and then this turbine will have to undergo lower temperature. Means it will encounter lower temperature. So actually, indirectly, it is for turbines only. The first stage turbine blades face the maximum temperature, so there is an upper limit to the temperature it can withstand. So to reduce the temperature, so then the turbine blades can tackle that temperature, it is needed, but it is not for directly cooling the turbine blades. It is to reduce the temperature so that the turbine blades can sustain that temperature. So after the combustion chamber, the combustion products go through multiple stages of turbine, where basically the flow loses its enthalpy. So the energy, because it was at very high energy after combustion, it was at very high temperature, it had very high energy. It loses its energy and rotates the turbine blades. And this rotation of turbine blades results in the rotation of the shaft, which is connected with the compressor stages. So the turbine blades actually run the compressors. So the amount of work that is generated by the turbine is equal to the amount of work that is required by the compressors, in this case for jet engines. No additional work is generated. Okay. So the expansion is done in such a way that only the amount of work that is needed for running the compressor is used. Rest of the energy still remains in the combustion products. Now these combustion products, which are still at high energy, means still at high enthalpy, still at high temperature, are expanded in a nozzle. So they are accelerated in a nozzle, and this energy, this static enthalpy or energy that was present in the combustion mixture, the combustion products, is converted to kinetic energy. So ultimately, the combustion products go out from the nozzle at a very high velocity. Typically, convergent nozzles are used for most aircraft because designing convergent divergent nozzle is very difficult. So convergent nozzle means yes.
Sorry, sir, I was a bit late. Internet issues. Nikhil, sir. Sorry. Can I get?
No problem.
Yes.
You can later go through the recording. Anyway, so the mostly for most applications, aircraft applications, the nozzles are convergent in nature. Okay, so the air goes out, or the combustion products goes out at either they will go out at sonic velocity, means in choked condition. We will discuss this later, or subsonic velocity relative to that temperature. Okay, sonic. Remember, sonic velocity can change. Means speed of sound depends on temperature. So the speed of sound at higher temperature is higher than the speed of sound at lower temperature. So here, because the temperature is higher, the speed of sound will also be higher. The exhaust products will go out at quite a bit of high velocity. Only in very high speed aircrafts, typically you will need to use a convergent divergent nozzle. It is not used even for military aircrafts because of other considerations, which we will discuss later. But if you have seen space shuttle nozzles, you will see that the nozzles are, it looks like they are divergent, means they are actually increasing in area. So actually they are convergent divergent nozzles. The convergent portion is hidden inside. You can only see the divergent portion. For space shuttles, it is needed because space shuttles, the velocity is very, very high, right? Although it is not a jet engine, it's a rocket engine, but the velocity is very, very high, and there you need a convergent divergent nozzle. For jet aircraft, typically only convergent nozzles are used. Unless, say, we are going for experimental aircraft in future, like scramjet or ramjet, where the velocity will be too high to use a convergent nozzle. So this is in short how jet engine, turbojet engine looks like or works. Okay. So turbojet engines are even used nowadays, but they are used mostly for military aircraft. So they operate at a very good efficiency at high speeds, at speeds around, say, Mach 2. So twice the speed of sound. They are very efficient. Okay. So in cases like where you need very high speed, like military aircraft, turbojets are used. For passenger aircraft, nowadays they are not used. They were used previously during 1950s and 60s, but they have been discontinued, and now turbofans are used, which we are going to take a look at next, because of the higher efficiency of turbofan engine at lower velocities. Okay, turbofan. So when I discuss about efficiency, actually we will study this later on in the course. It is not only the thermal efficiency, means it is not only the efficiency of how well the fuel is, the energy in the fuel is getting converted to, say, the work output or the propulsion. It is also, there is another efficiency which is known as propulsive efficiency. So how well is the kinetic energy being used up? So some, like the nozzle is generating kinetic energy, the engine is generating kinetic energy. How much of it is getting used up for actually moving the aircraft forward? That is a different thing. So it may happen that the exhaust occurs at a very high speed, but the aircraft is moving at very low velocity. So most of the energy is wasted in dissipation. So these things we will study later on. So my point here is that there are multiple efficiencies. So you cannot directly say that thermal efficiency is the most important parameter, because we have to also look at propulsive efficiency, which we will study later. So the propulsive efficiency, as we will see later, is good for turbojets at high speeds. When I say high speed, it's around Mach 2, so above sonic speed. So for supersonic aircraft, turbojets are very suitable. So that's why they are used for military aircraft. Previously, say, even supersonic passenger aircraft was there, very famous, Concorde. So that also used turbojet engines. It has now been discontinued after one serious accident that had occurred. And it was an old design, but it was a very, like, for that time, it was a very brilliant design, like passenger aircraft flying at twice the speed of sound. Nowadays, there are no aircraft like this. All passenger aircraft nowadays are subsonic. They just the cruise velocity is just below the sonic speed, around Mach 0.9 nowadays. Performance, all this we will discuss anyway later, because we will revisit these slides. So the second type of jet engine is known as turbofan. Okay. So the main problem with the turbojet engine is that they are not very efficient at lower velocities, moderate velocities, like just below the sonic velocity, at the subsonic level. And so for that velocities, what happens in the turbojet is that the exhaust speed is too high. Okay, and as a result, most of the energy is wasted as kinetic energy, which gets dissipated in the air. It is not used like properly for propelling the aircraft forward. So to increase the efficiency of propulsion, which is known as propulsive efficiency, again I am saying we will study this later, but briefly I am describing. You need the exhaust velocity to be as close to the aircraft velocity as possible. Okay, so that means that for a typically for an aircraft which is flying at Mach 0.9, you want the exhaust velocity to be much lower than that for a turbojet engine. So the way to do it is, one way is that you can reduce the exhaust velocity in the nozzle. Okay, you can design the nozzle so that the exhaust velocity is less. But in that case, if the nozzle area remains same or the mass flow rate remains same, your thrust will be reduced, because ultimately the thrust depends on the change in momentum. So the exhaust velocity will be reduced, mass flow rate will remain same, thrust will be reduced. Okay, you do not want to reduce thrust because you need very large thrust for large passenger aircraft. So the way around that was that setup like this was built, where there was a core part which is like the turbojet part, turbojet engine, and then there is a large outer duct. Okay. So through this large outer duct, large amount of air flows, and this is compressed by a fan or multiple fans, which are run by the turbines itself, similar to the compressors. Okay, so this large amount of air, which is known as the cold air, although it's not actually cold after compression, but relative to the air in the combustion region, this air is cold. So this exists through another nozzle, which is known as the cold nozzle. Okay, so they are accelerated by the fan, then they do not undergo any combustion. Okay, they just flow through the duct and then they accelerate through the nozzle. Okay, so this air goes out. This also goes out at relatively high velocity, but much less velocity as compared to the air which goes out from the core section, like the turbojet engine. The core section works like the turbojet engine that we have discussed right now. So this the other nozzle at the center is known as the hot nozzle, through which air goes out at very high velocity. Okay, and to the outer nozzle it goes out at low velocity. So the average velocity of exhaust is reduced significantly, and most of the mass flow rate of air occurs through the outer duct. Okay, so they are the ratio of the flow which occurs through the outer duct to the inner duct is known as bypass ratio. Typically, it is of the order of, for large passenger aircraft, it is of the order of 10. So around 10 times more air flows through the outer duct as compared to the inner duct. So the flow through the inner duct is still required because you need the combustion and the work output of the turbine to run the compressor and the fans. But it is only for that purpose. So most of the thrust is generated by the cold air because of their large mass flow rate. Okay. So what has happened in doing so is that you have reduced the average speed of the exhaust air and increased the mass flow rate of air because of more air is introduced in the engine. So the thrust is quite high, but the propulsive efficiency also increases. Okay. So these type of engines are very suitable at near the sonic velocity or just subsonic velocity, like Mach 0.85, 0.9, which is typical for very large passenger aircraft. All the passenger aircraft, jet aircraft that you board, say 2-engine aircraft. I think for most domestic aircraft, it is 2-engine aircraft. For large international aircraft, you might have 4-engine aircraft like say Boeing 747s or A380. So all these are turbofan engines, okay, very large turbofan engines. Any questions? We will discuss this in much more detail later on, but if you have any general questions, you can ask now.
Sir,
Yes.
sir, the combustion chamber is at a very high pressure compared to the compressor outlet. Is that correct, sir?
No. The compressor outlet is equal to the combustion chamber pressure, compressor outlet pressure. Because how will it increase? How will the pressure increase in the combustion chamber? Combustion chamber is open at both ends. It's like a duct, like a
Yes.
cylindrical pipe.
Yes.
So the increase in pressure occurs in the compressors stage by stage. So the final stage, we reach the maximum pressure of the cycle. So in the combustion chamber, ideally the pressure remains same. In reality, the pressure is slightly reduced because of turbulence and friction. A small, say 3 to 4% reduction in pressure occurs throughout the combustion, like flow through a pipe, you can say. But the
Yes.
pressure ideally remains same.
Okay.
So these are some like uh, examples of real life engines. This is the GNX engine. You can see the size of this engine relative to the persons who are standing. So this internal area that you can see is the core area. Outside of the core area, so all these wirings and other things are there. These are for fuel injection. A lot of things are there. It's a very complicated say engineering device. And this large outer periphery is for the cold air, okay, for the bypassed air. These are used for 787, like these are one of the largest engines nowadays in production, I think. These are used for large twin jet aircraft, large body twin jet aircraft. Large bodied aircraft means there are two aisles, means there are 3 rows of seats, and narrow bodies are with 2 rows of seats. Like the most of the domestic aircraft, you have 3 by 3 arrangement of seats. So those are narrow bodied aircrafts with 2 engines. So if you go with large body aircraft, you will see that there are 3 seats, then 4 seats, and 3 seats, or three seats like this. So even some of those aircrafts still use 2 engines, very large engines. Okay, some may use 4 engines, like A380, Airbus A380. Again, you can see the scale of this, and this is the fan. Okay, and internally you can see the compressor blades. I don't know if you are using a large screen, it will be visible to you. That small blades inside are compressor blades. This is again another view. This is the bypass region. Okay, these are the fan blades and the outer duct. Next time you board an aircraft from the rear side, you can take a look at the engine. Okay, you will be able to see the nozzles and all these regions clearly. Another example. Okay, these structures are known as chevrons. These are there to like to reduce the noise by modulating the turbulence of the air. This is from Air India. So this is the outer cold nozzle, and this small region here, this is the hot nozzle. This cone can actually move to change the cross-sectional area of the hot nozzle. Turbofans also have been used for other types of devices. So one interesting application that I'm just showing here is so this the moon landings that had occurred during 1960s and 70s by NASA. So they used a lunar module like this. Okay, so that actually did not use, obviously in absence of air you cannot use a jet engine, right? So all space applications use rocket engines because you need the oxidizer also to be carried on board, and jet engines need ambient air for running, so they cannot be used outside the atmosphere. So but to test this engine, it was difficult to test this engine in terrestrial condition on Earth because the gravity in moon is 1/6 of the gravity, approximately it is around 1/6 of the gravity on Earth. Okay, so if you are designing something to land on moon, you have to design in a different way, and you cannot do the experimental testing on Earth because of higher gravity. So somehow you have to negate that gravity, okay, 5/6 of the gravity, so that you have only say equivalent 1/6 gravity. So for that reason, these lunar landing vehicles used a turbofan engine, okay, to create a thrust in the opposite direction, opposite to the gravity, to actually cancel out 5/6 of the force of the gravity. So the equivalent force on them became equal to 1/6 of the gravity of Earth. Okay, so it was like the gravity of moon. And then they tested the, there are rockets which actually slow down the landing vehicle when it is about to land. They tested those things, okay, and the landing shock absorbers. So it has been used experimentally in this type of scenario also. Anyway, we will discuss this later on. So let me show you the third type of engines, which is very popular also. So turbojets are still very popular for military aircrafts. For civilian aircraft, they are not used much nowadays. They used to be used widely during 1950s and 60s, but now they have been replaced by turbofans. Okay. Turbofans are very widely used for most of the passenger aircrafts, large passenger aircrafts that you see. For small passenger aircrafts, where the velocity is still lower, say for shorter distances, so you want to go for a very short distance, okay, then the aircraft cannot go to very high velocity because it is limited by its acceleration. So you cannot give a very high acceleration to an aircraft because it will be very uncomfortable for the passengers. Okay, so for example, say you want to go from Mumbai to Pune, okay, which are two cities which are very nearby. So a very large turbofan aircraft, which can ideally operate at a cruise velocity of Mach 0.9, which is around say 900, 950 or 1000 kilometer per hour. It cannot reach the speed because the acceleration needed for reaching that speed for such a short distance will be too high for the passengers to bear. Okay, so if a turbofan operates at that distance, it will operate at a much lower peak velocity. So it will accelerate to a certain velocity, maybe 500 kilometer per hour, and again it will slow down. Okay, so the efficiency will be much reduced. Okay, so at those kind of velocities and those kind of distances, the highest efficiency is obtained by another sort of arrangement. So this type of engine is known as turboprop engine. I will discuss how it works, but this type of engine is known as turboprop engine, and they are very suited for small distances where you can accelerate the aircraft to only a moderate velocity, say 500 kilometer per hour, even slightly higher distance. Say for example, if I go from here to Kolkata, so I have boarded both types of flights because it is at the borderline of the distance for use of turbofan or turboprops. Okay, so turboprops are also quite efficient because the distance is around 450 kilometers, and turbofans are also quite efficient. So both types of aircrafts are used for this type of distances. If it was a shorter distance, turboprops would have been much more efficient. If it is a longer distance, I fly also regularly from here to Bangalore. So at those distances, you will not see many turboprop aircrafts, only turbofan large aircrafts you will see. Okay. So these turboprop aircrafts, how they work? So the most of the thrust is generated by a large propeller, which is outside this ducted region. Okay, this propeller is very large, even compared to the fan that is present in a turbofan. As compared to that, also it is larger, much larger. So it moves a very large amount of air, but at a very low velocity, relatively low velocity, as compared to the turbofan or turbojet. Okay. And this is run by the turbines. The other parts, inner parts are similar. So we have a compressor which compresses the air, then the combustion chambers, then the turbine. So this turbine work is sufficient to run the compressors as well as the propellers. So one stage may be running the compressor, couple of stages may be running the compressor, and couple of stages may be running the propeller, and they may be on single shaft or separate shaft. Typically, if they are on the same shaft, then the propeller speed needs to be reduced. So there is a reducing gearbox, okay, which reduces the rotational speed because the shaft rotates at very high speed. Compressor needs to rotate at very high speed, but you cannot rotate the propeller at this kind of high speeds because of the large size of the propellers. The edges of the propeller will go to supersonic speed, which will create very large stresses as well as very large amount of turbulence and reduce the efficiency of the aircraft. So you need the propeller tips to work at subsonic speeds. So you reduce the velocity. Okay. And then the exhaust goes up. Typically, for turboprop engines used in aircrafts, the exhaust will go out not like this. It will go out axially. Okay, and the small thrust that is generated by the exhaust. So most of the thrust, most of the energy is used up for running the propeller in this case. very small thrust is generated by the nozzle, very small amount relatively as compared to the propeller. Okay. This bending type of engine you will see in helicopters, okay, where because the engine is vertical, jet engine, this rotor, helicopter rotor is in the other direction. So this also creates a small amount of thrust for the helicopters also. Okay, if the flow goes out in the rear direction. Turboprops are used in many passenger aircrafts, very common in passenger aircrafts. You can see here. In pandemic situation, if you have boarded aircraft, you will see that much more number of turboprops are being used nowadays as compared to turbofans because of the low passenger counts. So typically these aircrafts are smaller size. So typical narrow-bodied aircrafts like A320 have 180 passenger seats, but these will have around 72 seats. So even smaller turboprops are there. But like if you go with the turboprop from Indigo or Air India, you will see that they have around 72 seats. Indigo actually cramps up to 80 seats, but the aircrafts are meant for 72 seats. And you can take a close look if you get a chance to fly. You will, because you will be boarding very close to, generally the boarding occurs from the back side. So you will be boarding very close to the propellers and engine. You can take a close look at the engine, what is happening. There is a small exhaust port here, very interesting to look at. Turboprops are also used for very large military aircrafts which need to operate at low velocities but need to generate very large amount of thrust at low velocities. Okay, like I forgot the name of this. In many movies you have seen actually this type of aircraft.
Mission Impossible, sir.
Yes.
ATR.
Many
Opening scene from Mission Impossible.
many movies. Yes, it's right. So all these are like they can take it, like they open from the back and they can these are cargo aircrafts which can take very large cargos. So you will find in many movies they are used. I have seen maybe at least dozens of movies which use them. Okay, not only say Mission Impossible, any of the movies, many of the movies use them. So they are actually you need to operate them. You do not need them to operate at supersonic speed, but at low speed you need high efficiency and thrust. And in those cases, turboprops are very useful. Okay, so they are very large. They open from the back and even can carry tanks and other things because of the large cargo space that is present.
So
Yes.
So the turboprop aircrafts are already smaller in size and require and are not like too fast in velocity. So why can't we directly use IC engines in place of this?
Because of still IC engines. See, why jet engines have replaced IC engines? Jet engines have replaced IC engines because jet engines have much better thrust to weight ratio. Okay, so if you want to use IC engines, if you take a look at IC engines, so obviously you need to generate very large amount of power as compared to cars or automobiles or an aircraft to lift an aircraft. So the engines will be of very large sizes. Okay, and their weights will be very large as compared to jet engines for the same amount of thrust. So the weight to the thrust to weight ratio is not favorable for IC engines. That's why they are not used. Okay, and jet engines operate also at very high efficiencies typically. So IC engines are not preferred. So they are not used anymore at all in any aircraft. They went obsolete long time back.
No, sir. But in case of turboprop engines specifically,
I cannot hear you.
converting into the rotation motion of this propeller, right?
Turboprops. See, yes. Can you repeat your question? I could not hear properly. Voice got cut off.
Someone muted me. Yeah. So in turboprop we are not using the jet thrust.
Correct.
Yeah.
Yes.
So we are
jet
just
thrust is, yes. So the thrust is not the only thing. The turbine is converting the energy very efficiently for running the propeller. Okay. So the weight of the turbine and weight of this jet engine, okay, to generate the thrust is still being generated, right? The thrust is generated by the propeller. So for the same thrust, the weight of the engine, if it is a turbine and like it is a jet engine, will be much less as compared to the engine, as compared to the weight of the engine that will be required if you have multiple IC engines. So you will need say 10, 12 reciprocating engines arranged around the periphery, and that weight will be much larger, and it will also take a large cross-sectional area. So it is not a, see, jet engines are like, the motion itself is more suited towards this type of rotary motion, right? Because of the rotation of the shafts. In IC engine, you are converting a linear motion to a rotary motion. Okay. Obviously, still they are used for automobiles, because automobiles move at very low speeds as compared to aircraft and need very less power as compared to aircraft. But for this type of, when you go to this kind of scales or this type of power requirement, particularly because you need to carry that weight, because you need to lift whatever additional weight is there, that becomes, then the flight becomes much more challenging. So you do not want to have any excess weight, right? So that's why you do not use IC engines at all in any applications nowadays. IC engines were used to run propellers previously, but nowadays all propeller based engines actually use gas turbines to run them.
Okay, sir.
Other aircraft applications are also there. For example, this is a VTOL aircraft, okay, vertical takeoff and landing, and where the engines can actually change, it means it can rotate, change the direction. So for takeoff, it is in a vertical direction, so that it does not require any runway for takeoff. It can just take off from very short distance, or even like a fully static position. So for those cases also, because of the very large amount of thrust that is generated at low speed, turboprops are used. Some other experimental types or actually prototypes have been built, but not used widely, because like propeller at the back, because of stability issues and other issues. If you're pushing something from the back, it is not as stable as if you are pulling it from the front. You can, if say, you can take an extreme, if you take a pencil and pull it from the front, it will move smoothly. If you try to push it, it will become unstable. So anyway, so these three are the most widely used aircraft engines nowadays. Okay, and if you see any military aircraft, so the only thing is that why not civilian aircraft fly at supersonic speed? That is the only question that you can ask. So then we can use even turbojets for civilian aircraft. So the main reason is that, so even throughout the history, it's not that we could not design supersonic passenger aircraft, but supersonic aircraft had a lot of challenges, particularly if they fly over heavy civilian areas. See, when the transition from the subsonic to the supersonic region, very large amount of noise is created. The sonic boom is created that can be felt by the residents. So generally, military aircraft, when they operate, this type of change from the subsonic to the supersonic speed is prohibited in heavy residential areas. So there are areas which are demarcated, or regions which are demarcated, where you cannot go supersonic. So military aircraft follow those type of rules. Even for civilian aircraft like Concorde, they used to fly subsonic till they passed over the land border, means till they passed over to the ocean from UK, and then over the ocean they used to go to supersonic speeds. So it will create huge amount of noise, and practically it is not convenient to use supersonic aircraft. And the distances, so theoretically it is possible to use for large distances, but still turbofans have even larger efficiency, and they operate at their best when it is just subsonic. Okay, so that's why supersonic passenger aircraft are not used. But for military purposes, you need very high speed for during certain maneuvers, like when you are engaging another aircraft or want to evade a missile. So you need very large amount of speed, and at that time, turbojet engines make more sense. So apart from this, there have been some other engines which are not used widely for the civilian or military aircraft, but have been designed and used experimentally and for other applications sometimes, okay, like for using cruise missiles. So one type of aircraft which is quite popular is not aircraft, sorry, engine, which is quite popular is ramjet engines. Okay, they are used from 1960 onwards for cruise missiles, where there is like there are no passengers basically, so there is no issue with any like passenger comfort, anything. You need very high speed, and you need a very simple device to go to a very high speed. So very ideally suited for high speed missiles. So what is the working principle of ramjet? Again, we will discuss this later, and we will go into mathematical details also, but let me just explain briefly. So ramjets typically operate at very high speeds. So they are very efficient at around Mach 3 or slightly higher velocity. Okay, so 3 times the speed of sound. So at these speeds, the incoming air has such a high kinetic energy that in the diffuser itself, if you compress them, if you convert the kinetic energy to enthalpy and pressure, there is a large increase in pressure. Okay, because of the very large inlet velocity. So in these cases, you have a convergent divergent diffuser. Okay, convergent part is for the supersonic speed. Convergent means the diffuser needs to be convergent. The area needs to decrease. If you are at supersonic speed, just a second. Okay, so if you are at supersonic speed, the area needs to decrease. Okay, for a diffuser, which is counterintuitive. We feel always, based on our common day-to-day activities, we see that when the area is decreasing, the speed increases. But at supersonic speed, the opposite behavior is true. If the area increases, the speed increases. If the area decreases, the speed decreases. So up to the sonic speed, the area decreases, and then there is a diverging section where the speed further decreases in the subsonic region. Okay. So this is sufficient enough so that no compressors are required at all. Okay. The compression due to the diffuser itself is sufficient to increase the pressure to a very high value. And because there are no compressors, then you do not need any turbines also, because turbines were only present to run the compressors. So if there are no compressors, what is the need of turbines? So we do not need any turbines also. Okay. So then directly you have some combustion chambers. Combustion chambers need to be tricky to build, because you need to sustain the flame at those high speeds. The speed is still subsonic, but still flow is going out at quite high speed. And if you do not design the combustion chamber properly, the flame will blow out, means the flame will go out with the flow. So you have regions where locally the velocity is very small. Okay, secluded regions like this. Okay. So that the flame can be sustained. So after the combustion, the temperature of the pressure does not increase. The temperature of the fluid increases to a very high value. And here there is no limitation of how high the temperature can go, because you do not have a turbine. You are not restricted by the turbine blade material. Okay, nozzles can withstand lot of very high temperatures. Okay, because the nozzles are not rotating. Turbine blades, the main problem was not that the turbine blades will melt. We will study later. The main problem is that they are rotating at high speed, and what happens is that because there is so much stress, centrifugal stress on them at high speed, they tend to elongate, and this happens much faster at a higher temperature. This is known as creep, and that was the main problem. So once you have removed the turbine, you have no problems with high temperature. So you can go to very high temperature and then use a nozzle, to a convergent divergent nozzle, as you can see here, to increase the velocity to very high value and generate large amount of thrust. So this is a very simple device, because there are no moving part. Very simple device. Yes.
So you just said about creep in the turbine section.
In the turbine blades, creep is the major problem for the turbine blades. Turbine blades are rotating at very high speed, right? So this we will discuss later on. I have the slides actually, but we will discuss this later on. Let me just give reference to. So this, where is any picture is there of? Let me see. Okay, so these turbine blades are there, right, at the back. they are rotating at very high speed. So they are undergoing large amount of stress in the longitudinal direction because of centrifugal action, right? So, and so they are under large stress, and if you are at a high temperature at a constant stress, the creep will be higher. So creep is the, say, at a constant stress with time elongation occurs, right? So because they are undergoing high stresses and for a long duration during the flight, at high temperature, because the creep is a very prominent phenomenon, the length of the turbine blades will tend to increase and they will clash with the outer casing, resulting in catastrophic failure of the engine. Very, very dangerous thing. So they are designed very carefully so that the creep is very limited. So it is not that the melting temperature is a problem. Melting temperature is very high, 1900, 2000 degrees centigrade for nickel-based alloys. But the creep limits the temperature to around 1200. Nowadays, modern aircraft with a lot of cooling and a lot of like single blades, single grain blades, single crystal blades, and directional certification, they are limited to 1100, 1200 degrees centigrade. What is your question?
Sir, exactly in ramjet,
Yes.
you say, why did we come to turbines, and is it how this starts?
No. I'm saying that in ramjets there are no turbines. That's why we can go to very high temperatures. Because there is no turbines, you are not restricted by the presence of turbine blades. So that's why it's a very simple device, right? There are no turbines and compressors. So you can go to very high temperature. You want very high temperature, right? Because then you can generate very high thrust. Because higher the temperature, higher is the energy carried by the fluid, enthalpy carried by the fluid. And you, if you know basic thermodynamics, you know that this enthalpy plus like if you have a simple process, expansion in a nozzle, first law of thermodynamics says that it's like in the absence of other changes of energy, potential energy and other energies. So H plus V square by 2, enthalpy plus kinetic energy remains constant. Okay. So if you have very high enthalpy, at this point, obviously, we'll have very low kinetic energy. You can convert that high enthalpy to very high kinetic energy. So you can generate very large amount of thrust in ramjets as compared to jets where you have turbines. That is what my point was, that it is actually a positive thing that there are no turbines here, because then you can generate larger thrust. So that's why you can fly at very high velocities, because you can generate larger thrust.
Yes, sir, but how does it start, sir? From
That's the good point. I was going to ask. Okay, what is the limitation of this engine? What is the limitation of this engine? Why are not
zero?
sorry?
It won't start from zero velocity. So
Correct. Yes, it's a good point. I was actually going to ask that question. It cannot operate at low velocities because the compression is not sufficient. It cannot start from zero velocity and it cannot operate at low velocity because the compression is not sufficient to actually make the engine work properly. They only work properly at very high velocity. Theoretically, they can work from Mach 0.5 onwards, but they are at their most efficient at Mach 3. Okay, Mach 3 velocity. So they need something else to propel them to those velocities. So because they are not used for passenger aircrafts or other aircraft, generally they use some sort of booster rockets for missiles. Okay, they use some sort of booster rockets to start. The rockets can operate from zero velocity. So the rockets will propel them to a high velocity, and then the jet engine takes over. The main advantage of jet engine what is the main advantage of a jet engine as compared to a rocket?
So you won't carry any oxidizers.
Correct.
Right?
So the weight will be much reduced, right? Because the oxidizer is, for jet engine, you are just using ambient air. For rockets, you need to carry the oxidizer. So the weight of a jet engine will be much reduced, overall weight. So only for the starting part, a rocket is used, then the jet engine takes over. And these are only used for, till now at least, they have been only used for military applications, like for operating missiles and for prototypes. Okay, but not actually for any aircrafts. So now, say I want to increase keep on increasing again we will study this later on. is this clear? Like, or any other questions are there about scramjets? What is the time? Any other questions are there?
No, sir.
Okay, so if I want to design an aircraft for even higher velocity, if I keep on increasing the so what I will need to do, say if you have a very high velocity, say not Mach 3, say I want Mach 6 or Mach 7, a very high velocity. So the incoming air will come at a very high speed, and if you want to reduce the speed to subsonic speed, it is lot of losses will occur. Okay, it's not very easy to reduce from that kind of speed. Okay, and what needs to be done in those cases is that you want the speed to be still very high. You don't want to waste that means energy that was present through turbulence and other losses, frictional losses. So you want to maintain that, sustain that, means you will reduce the speed, but not to subsonic level. So still you want to still carry a very high velocity in the combustion chamber. Okay, not at the subsonic speed, but still at the supersonic speed. So this type of aircraft where the flow in the combustion chamber is at supersonic speed are known as supersonic combustion ramjet engines or scramjet engines. Okay, so they are in principle exactly same as ramjets. The only difference is that the combustion occurs at supersonic speed, and it's a very difficult task because the velocity is so large in the combustion chamber that the tendency of the flame blowing out is very large. So you need very careful turbulence setup and like mixing so that you can sustain the flame there. We will have a brief discussion on this later when we discuss about scramjet engines. But these combustion chambers are designed in a very careful way to sustain the flame at supersonic speed, because it is very difficult to do that through proper use of turbulence. Okay, I think I have some. We will discuss this later mainly, but just to show you how it looks like. So this type of shocks and other like bore shocks and barrel shocks are generated, which actually keeps the flame sustained in a small region. Okay, in scramjet engines. We'll discuss this in more depth later on in the second half of the course, towards the end of the course. So these scramjets can operate at, theoretically they can operate at very large speeds, Mach 7, Mach 8, Mach 2, Mach 10, but only experimental prototypes have been like used till now. So this is one example. This is from long back, I think early 2000. I don't remember the year. NASA X-43. So again, there need to be, obviously the same limitation is still there, right? Because it's still a ramjet engine. It's only supersonic combustion ramjet. So they need to be taken to a high speed, and only then this scramjet is started. Okay, so typically they are taken to a high speed using. So for these experimental purposes, they used another aircraft. These are very small aircraft prototypes. So very large aircraft was used, which carried this small aircraft to a large speed, and then this was released, and it flew for a few seconds. Even India has also developed their own scramjets. You might have read about, or you can read about. ISRO has successfully tested scramjet engines in 2016, I think, using a rocket engine to take it to a high speed. And DRDO has also tested more recently in 2019 scramjet engines. I don't know further details, but you can get them. Details are available. So, but till now they are not used. So there are plans to use them in the long run, but till now they are no use. At least they have not been used for any large scale applications. But theoretically, they can be used up to Mach 10 speed for very large distances. It will be very helpful. Okay. There is another type of aircraft which has fallen out of favor. This is the last type that we are going to study. This we will study just for historical reasons. Okay, this became popular long back during the World War time. Okay. This is known as pulse jet engine. So these also do not have any compressors, as well as, because there are no compressors, there is no need for any turbine. Remember, for jet engine, turbines are only there to run the compressors or propeller. Okay. So the main difference here was that these used some sort of valves, okay, reed valves. So this operated more like somewhat like an IC engine, okay, partially. So what happens? There was an air intake, then the valve would close because of the combustion pressure, and combustion will occur, and the exhaust will occur. And once the exhaust gas goes out, because of the inertia, I mean, partial vacuum is created. Again, the valve opens, and again some air comes in. Again, some fuel is injected. Again, combustion occurs. So here, this is the only jet engine that we are studying where the combustion is not continuous. It occurs in pulses. Okay, it's like a cyclic motion, like intake, then combustion, then exhaust, intake, combustion, exhaust, like this. Okay, so this type of engines, what is the, can you tell what is the main advantage? What will be a big advantage of this engine as compared to ramjet engines?
So can start from zero velocity.
Yes, they can operate at low speeds. Okay, they can operate at low speeds, because at low speeds also they can increase the pressure. What will happen? The valve will close, and during the combustion itself, this region is very narrow, so it is like a constricted area. So it is like a combustion in an enclosed area, like an IC engine. So the pressure will increase during the combustion. Okay, it is more like a constant volume, constant pressure combustion. So pressure will increase, and that can be used for then expansion in the nozzle. So they are very suitable for low speed, like below Mach 0.5. But there were a lot of practical difficulties with these engines. One was that these valves could not operate for long duration. Their life was only few hours. And at those times, it was fine, like during the World War times, because World War One or around 1920s, 30s, because you needed aircraft for very short durations, more like use and throw, okay, because of very low reliability. So, but nowadays it is not useful at all. And second is that they also have. So the main problem was still was with the valves, which could not sustain this kind of long high temperature application. And another problem is the very large amount of noise that is created, okay, because of this pulse combustion that occurs. So they are not used anymore. Nowadays, very recently, again, researchers started in this area with valveless, without any valves, but with the same principle, by properly designing the combustion chamber in such a way so that using acoustic reflection itself, you can block the movement of the air in the backward direction. Okay, we will discuss this later on. You sometimes they use U-shaped pipes, okay, so that the air does not flow. The air can only go in one direction, but there are no valves. So these are being nowadays again studied, but not used till anywhere. Okay. So these are the different types of engines. So last thing that I will just mention here before we go into the actual, we will actually start our course is afterburners. Okay, so I guess most of you know what are afterburners, but let me explain. So in many applications, typically military aircraft, you need very large amount of thrust for a very short duration. What can be some occasions, like when the aircraft is taking off from a very short distance, like from a aircraft carrier where the runway is very short. So you need the takeoff thrust to be very large. Again, another occasion can be when, say, your aircraft is trying to evade a missile, or you are in active combat with another aircraft. Okay, in those cases, you are very worried about very high speed or very high thrust, very large acceleration, but you are not worried about fuel efficiency. Okay, so in those cases, what can be done is there can be secondary combustion chambers. It's actually not a proper combustion chamber. There is secondary combustion which occurs in a long pipe, a long tube, which is known as jet pipe or afterburner, which is after the turbine stages. Okay, so let me just quickly explain the principle of this. So you have the compressors again, similar to turbojet engines. So this is a turbo fan with afterburner, but you can have turbojets also with afterburner. Let me just explain the thing. So you have compressors, then the combustion chambers, and then there are turbines. So turbines are used for running the compressor. So after the turbines, the combustion products still have quite a high enthalpy, and if we accelerate them through a nozzle, it will be like a normal turbojet or a turbofan engine. We will generate thrust. But because very large amount of air fuel ratio is used, lot of unused oxygen is still present in the air fuel mixture here, or the combustion products here. Okay, lot of oxygen is still present. So what is done is that there are secondary injectors here. There are fuel injectors here, which inject fuel, and this is ignited, and again the temperature of the air fuel mixture, the combustion products is raised to a very high temperature. Now this temperature can be raised to very large temperature because there are no subsequent turbine blades. Okay, so we are not limited by the turbine blade temperature. So we can raise the temperature to very high temperature, as high as the nozzles can withstand, and then it can, this very high enthalpy fluid can be expanded through the nozzle to generate very large amount of thrust. The only problem is that the efficiency for this is quite low, okay, as compared to a typical turbojet engine. The efficiency when you are using afterburner is quite low. So they are used for short distances. They will burn up a lot of fuel. They are used for short distances for a very short amount of times, but when it is necessary, and they are used in, and they can generate very large amount of thrust for those short distances. They are used both for turbojets as also they can be used for turbofan engines. Okay, this is a low bypass turbofan. We will read about this type of engines later. So the amount of cold air that is passing actually is very low. You cannot see it properly, but there is a small gap between the core section and the outer casing to where the cold air is passing. And generally, both the airs actually get mixed together, hot air and cold air, and then the afterburner section is there to increase the thrust. Okay. So, and when the afterburner runs, you will be able to see actually that glow in the engines. Means because the flame is at a such high temperature, it is actually glowing, and you can see the engines, like the exhausts themselves are glowing if the afterburners are working. Okay. So anyway, we will revisit this thermodynamics and all this later on. But my idea was to give you a brief glimpse of different types of engines, so that when we go through the engines, you feel more comfortable about connecting the discussion to the practical aspects of the engine. Anyway, we will again revisit these slides later also when we go to the thermodynamics of this. Any questions?
No, sir.
Okay, so let us take a small break then, 5 minutes, and then we will continue this. We'll start with the actual course. Okay. Okay, so we will continue. Am I audible?
Yes, sir.
Yes, sir.
Okay. So we will start with thermodynamics analysis of industrial gas turbines first, and then we will go into the details of jet engine. Each of the jet engine we have to discuss in detail. And these two parts, the industrial gas turbines, then the jet engines, will actually take us more than halfway through the course. This is the major part of the course. So after the mid-sem, sometime after the mid-sem, it will continue. And in the second half of the course, which is shorter part, we will discuss about the individual components, working of the individual components like compressors, combustion chamber, and turbine. So the first part actually is quite large. Okay. So again, for the industrial gas turbines, first we will start with ideal cycles, and then we will go into details of real cycles, means with losses and with non-isentropic processes, things like that. Okay. And we will also see how these things affect the efficiency and efficiency of the cycle and the net work output from the cycle. Anyway, so we have already discussed about applications of gas turbines. I have summarized it here. So they are used for power generation for gas turbine plants and mainly for aircraft propulsion. Other applications are there in marine propulsion, land propulsion. Experimental micro turbines have been built for small scale power generation, but not used much. Then types of gas turbines, industrial gas turbines, which are used for generating shaft power. Yes, please switch off your mic. Industrial gas turbines, which are used for generating shaft power. So they are basically run a generator to generate electrical power. Then turbojets, turbofan, turboprops. Okay. So ideally, ramjets and scramjets are not exactly gas turbines, but they are jet engines, and we will study them as part of the jet engines. Okay. Pulse also is not actually a gas turbine. They don't have any turbines, but we will study them as part of these jet engines. So I should not write types of gas turbine here. Maybe I will remove the next time. Components, there are three major components. We have already discussed again. Compressors needed for expansion in the turbine. So for expansion in the turbine, we need a pressure ratio. Now the outlet pressure of the turbine is fixed. Say if it is an industrial turbine, you know that the outlet pressure is equal to the ambient pressure. So the pressure at the inlet of the turbine must be higher. So to get that high pressure, we need to compress the air. As a result, compressor is required. Okay. Combustion is required for actually increasing the enthalpy of the fluid, which is working fluid. Because without any heat addition, you will not get any net work output. So to get work output, you need to add that energy. So combustion chamber is present because of that. And turbine is obviously required for work generation. Okay, some of the work is used for running the compressor. Rest of it is used for running the generator. Again, we can demarcate gas turbine cycles as shaft power cycles. So if you go to cycle analysis, shaft power cycles, which are for industrial gas turbines, and propulsion cycles, which are for turbojet, turbofan, turboprop, ramjet engines, scramjet. Okay. So what is the main difference between these two types of cycles? For propulsion cycles, the speed of air is also very important. The kinetic energy of air, both the incoming air as well as the outgoing air, and needs to be taken into consideration. However, for shaft power cycles, we can ignore the kinetic energy or change in kinetic energy of the air. Although there is small change in kinetic energy of the air, we typically ignore it because it does not contribute much to the change in the power output. Okay. So what we are going to do is we are going to start with ideal shaft power cycles, ideal industrial gas turbine cycles. Okay. So all of you must have studied in detail Brayton cycles, okay, in your thermodynamics or advanced thermodynamics course, or some course you must have studied Brayton cycles. So the basic cycle for gas turbine is the Brayton cycle. We will again study just for a revision, but it will be like a revision for you guys because we have already studied this. So the ideal cycle for gas turbine is known as a Brayton cycle and is developed using certain assumptions. What are these assumptions? We assume that the compression and the expansion processes are reversible adiabatic. Okay, in general, they will be adiabatic processes because they are very fast processes. But we are assuming additionally that they are reversible. It means that they are isentropic processes. Okay, entropy remains constant. Second important assumption is that we are assuming that kinetic energy change is negligible, as I have already discussed. Then we are assuming that this is an ideal gas. Okay, so we can use ideal gas laws, and the properties are constant. They do not vary with temperature. In real life, the properties will change with temperature as well as change with composition, because the composition also changes, right? So initially we have just air from the atmosphere, but after combustion, now the properties will change because now we have a mixture of air plus carbon dioxide plus water vapor. So all the Cp, Cv values should change, and our calculations and gamma also will change. So our calculations we will have to, means in real life the calculation needs to take that into account, and we will do that later on. But at this point we will just assume that they are ideal gas, which we will assume to be air, okay, with constant Cp and Cv. Then another major assumption is that there are no pressure losses and frictional losses. So we have already assumed that there are no frictional losses in the fluid in the compression and expansion because we have assumed that to be isentropic process. But there are no additional pressure losses in the combustion chamber or due to friction or due to turbulence mixing. Okay, so that is another important assumption. In real life, there will be around 3 to 4% pressure decrease in the combustion chamber. And another major assumption, not major assumption, but another assumption is that mass flow rate remains constant. So in real life, the mass flow rate will increase by around 2% after the combustion chamber because you are introducing fuel. So the mass of the fuel also needs to be taken into account. Okay, and the fuel air ratio is typically of the order of 1:50. So say for 1 kg or 100 kg of per second of air, you will introduce 2 kg per second of fuel. So the combustion products mass flow rate will be 102 kg per second. So there is a 2% increase, typically around that 2 to 3% increase. So that we are neglecting at this point. Later we will also use that in our calculations. So later you will see that one by one we will remove all these assumptions and we will do the calculations for very realistic cycles. Okay. But at this point, let us focus on the ideal cycle to get the fundamental things correct or to understand the fundamental things. Okay, so with this assumption, this is a typical schematic diagram of a gas turbine cycle. We have the compressor. Compressor is shown like this, like a conical object. This is standard practice. You should not show it like a box. Okay, why it is shown like this? Because the cross-sectional area is decreasing in the compressor because the mass flow rate remains same, and due to increase in pressure, the specific volume of air is decreasing. So we need lesser amount of area, cross-sectional area, for the same mass flow rate. So the cross-sectional area decreases. So it is shown schematically like this. So air enters at condition 1, ambient condition 1, and then it goes out of the combustion chamber compressor at condition 2, okay, which is at high pressure and temperature. Then it passes through the combustion chamber where the heat input occurs. Okay, so at this point we will assume that the combustion process is idealistic, so all the energy is getting converted to it. Later on we will actually use a combustion efficiency. So typically for jet engines, combustion efficiency is very high, of the order of 98-99%. So most of the energy is actually utilized, unlike IC engines where the combustion efficiency is much lower. Okay, because in gas turbines we use very lean mixture. So there is lot of excess air that is available for combustion to occur. Then after the combustion chamber, the combustion products, which is a mixture of carbon dioxide, water vapor, oxygen and nitrogen goes out at a very high temperature. Pressure remains same as the outlet of the compressor. Okay, for the ideal case. So this heat addition is a constant pressure heat addition. Okay. First process is an isentropic compression. Second process is a constant pressure heat addition. Then this high temperature, high pressure fluid is expanded in the turbine. So turbines are schematically shown like this. You should also draw like this, because the cross-sectional area increases along the length of the turbine because the specific volume increases. So for the same mass flow rate, you need larger cross-sectional area. Excuse me for a second. All right, let's continue. Actually, I have some throat infection which is causing some trouble. Anyway, so after the expansion in the turbine, the enthalpy of the fluid is reduced. So the entire enthalpy is used up as work output. Some of the work is used for running the compressor, and rest of it is used for, means goes out of the cycle. It is used, the shaft is connected to the generator shaft. It is used for running the generator. Just a second again. I'm not feeling so good. Okay, let us continue. So finally, the combustion products come out at a lower temperature and pressure. Okay, pressure will be generally, if you want to use the full potential of like how much work can be extracted. So for industrial gas turbines, the air will come out, combustion products will come out at atmospheric pressure. Okay, you cannot go below atmospheric pressure, obviously, then there will be backflow. So the minimum pressure that you can go at the exhaust is atmospheric pressure. And temperature will still be higher than the atmospheric temperature. Okay, so we will see in the cycle how it looks like, but temperature is still higher. So a lot of unused energy is still there in the exhaust gases, which is lost in the atmosphere. Okay, because you cannot expand it below the atmospheric pressure. So this is how a typical gas turbine cycle looks like schematically. This is an open cycle because we just pull in air constantly and use it for combustion, and then it is exhausted out. The same thing, the same working fluid cannot be recirculated here. Unlike steam turbines, where the same steam is recirculated again and again. In this case, obviously, because combustion is occurring internally, unlike steam turbines, that the combustion is occurring internally, you cannot circulate the same product again and again. You will run out of it. You need fresh air for the combustion to occur. So this is an open cycle. So what is done to study this open cycle in a better way is that we close the cycle. So we know that the condition 4 here is at atmospheric pressure, which is equal to the pressure at the inlet condition. Okay. However, the temperature here is higher than the inlet temperature. So we connect it through a additional process as if some heat loss is occurring at constant pressure. Okay. So as if there is a heat exchange occurring at a constant pressure, so that the temperature comes back to the initial temperature. So by doing this, we can develop a closed cycle like this. Okay. By putting a hypothetical heat exchanger, we can develop a closed cycle, so that the temperature of the working fluid comes back to 1. And we use it at this point. We are not studying using proper combustion and all, right? We are just assuming that it is air which is flowing through, so we can study it like a closed loop. But in real life, you cannot obviously use this type of arrangement. But this is just for thermodynamic calculation we are assuming that the same air is getting circulated again and again, and this extra energy that was present here is lost out to the atmosphere by using a heat exchanger, okay, which brings the temperature down to the inlet temperature. So the maximum temperature in the cycle occurs at this point 3 after the combustion chamber, and the minimum temperature in the cycle occurs at this point 1, which is the ambient temperature. So this is known as the closed cycle, and this is the standard Brayton cycle that you have studied previously. Okay. So how does this look like? So 1 to 2 process, which is the compression in the compressor, is an isentropic process. So in the TS diagram, this is an isentropic compression. So temperature increases, entropy remains constant. We go from 1 to 2. Okay. Then we have a constant pressure heat addition from 2 to 3. So this is a constant pressure line in a TS diagram. The slope increases upwards, and this actually shows the constant pressure heat addition. Entropy increases during this because of heat addition. Then there is an isentropic expansion. So the entropy remains constant, and because of the expansion, the temperature decreases. So the temperature goes down like this, and you come back to the same pressure as the inlet pressure. So again, this is another constant pressure line, and we are assuming that the cycle is closed using the constant pressure line, constant pressure heat rejection from 4 to 1. Okay. So the heat addition we can denote it as Q in, and heat rejection we can denote it as Q out. Okay. What will be the work input? Work input to the compressor is H2 minus H1, change in enthalpy that is occurring in the compressor. Work output from the turbine is H3 minus H4. Okay, change in enthalpy in the turbine. Energy input in the combustion chamber is H3 minus H2. Okay, so the energy increase that is occurring in the combustion chamber. This is equal to H3 minus H2. I think these things should be very familiar to you. You might have forgotten or might not remember. Otherwise, this should be very familiar for all students. So the same diagram, if you want to draw in a PV diagram, sometimes students actually, when I give them to draw a PV diagram or other types of diagram, they falter. They because their understanding is not clear. So you should be able to draw this cycle in any sort of diagram. It's not that you just memorize the TS diagram. Okay. So you know what are the individual processes. Then you should be able to figure out how they look like in any type of thermodynamic diagram. So in a PV diagram, the constant, like isentropic compression, will look like this 1 to 2. So it's a isentropic line, and the pressure is increasing, right? And because it's a compression, specific volume is decreasing. Then we have a constant pressure heat addition from 2 to 3. Then isentropic expansion from 3 to 4. Okay. These are not straight lines, these are curved lines, although it looks like straight lines the way I have drawn. And this 4 to 1 is again a straight line. This is the constant pressure heat rejection. And these are very simple calculations for the cycles are very simple, right? Because we are using just ideal gas. So unlike steam turbines, here we can do a lot of calculations very quickly. That is one advantage of working with at least studying gas turbines, or while studying gas turbine, we can solve the problems much more easily without using any charts and tables. Because for everything we can assume ideal gas loss with known Cp and Cv values. So the work input, as I was saying, compressor work input is Cp T2 minus T1, okay, H2 minus H1. So turbine work output is Cp T3 minus T4. Obviously, we are assuming at this point that Cp is constant. We have taken that assumption. Later, we will see that Cp for turbine output is different from Cp for compressor input. Because in one case, you have air at a low temperature, relatively low temperature. In another case, you have combustion products at a higher temperature. Then heat addition is Cp T3 minus T2. Okay, so the net output is Wt minus Wc, Cp T3 minus T4 minus Cp T2 minus T1. So we can get the efficiency. Again, very standard efficiency eta is equal to work output, net work output by the heat addition in the combustion chamber. So Cp T3 minus T4 minus Cp T2 minus T1 by Cp T3 minus T2. Let me just I want to keep the cycle open. Okay. So now after some simplification, so CP gets cancelled, and you can rearrange the terms. So you can rearrange them as T3 minus T2 minus T4 minus T1. So we can write this as 1 minus T4 minus T1 by T3 minus T2. If you take out T1 by T2 as common, so on the numerator you get T4 by T1 minus 1, and in the denominator you get T3 by T2 minus 1. Okay. So for further simplification, we can calculate based on the pressure ratio. Pressure ratio is the ratio of pressure across the compressor, and it is a design parameter. We will study later what are so design parameters are parameters which the engineer gives, means which are the basic parameters while designing a cycle. So design parameters which needs to be decided before designing a engine or a cycle is one of the design parameters is the compressor pressure ratio. Before and based on experience or previous calculation, previous models, these are decided what will be the compressor pressure ratio. Typically for modern aircraft, it's around 20 or more than 20. And the other design parameter is turbine inlet temperature. So that is based on the material of the turbine blades and the cooling of the turbine blades. So the maximum temperature is also fixed. So these are the two design parameters which needs to be fixed for designing the cycle. And obviously the ambient conditions are also fixed. So temperature and pressure at one are also known. Okay. So if we know this, we can describe the, or we can draw the cycle and can do all the calculations. So T2 by T1 is equal to, because it's an isentropic process, we can write this as equal to P2 by P1 to the power gamma minus 1 by gamma, where gamma is the ratio of the specific heats. For here it is 1.4. We will be assuming here for this ideal cycles. Okay, and this pressure ratio is denoted by R. Okay, so this is equal to R to the power gamma minus 1 by gamma. T3 by T4 is also, so P3 is equal to P2 because it's a constant pressure process, and P4 is equal to P1 because this is also a constant pressure process. So T3 by T4 is equal to P3 by P4, and P3 by P4, sorry, T3 by T4 is equal to P3 by P4 to the power gamma minus 1 by gamma, and P3 by P4 is nothing but equal to P2 by P1. So this is again same as R to the power gamma minus 1 by gamma. So we can simplify this as T2 by T1 is equal to T3 by T4, or just by rearranging T3 by T2 is equal to T4 by T1. Okay. So in this calculation, you can see that T3 by T2 is equal to T4 by T1. So the entire terms within the bracket cancels each other. So our efficiency then is equal to 1 minus T1 by T2. Okay, this is the expression of efficiency. And 1 minus T1 by T2 is equal to 1 minus 1 by T2 by T1, which is 1 minus 1 by R to the power gamma minus 1 by gamma. This you must be very familiar. This is a very well-known expression for efficiency of Brayton cycle. Okay. So the efficiency for a given gas, for air, obviously gamma is fixed. So the efficiency will depend on the compression ratio, compressor pressure ratio. For if there is no compression, R is 1 and the efficiency is 0. If you keep on increasing the value of R, you will see that ideally the efficiency keeps on increasing. This is not the case for all engines. This is for this basic standard Brayton cycle. Okay, later we will see that for other types of cycles, efficiency may not always increase with R. Okay, so in this case, if you keep on increasing R, this denominator will keep on increasing. So this total term will decrease. So 1 minus the total term will increase. So the theoretical limit, at the limit, you can go to very high efficiencies. Okay. So this, if we plot efficiency versus R, it will look like this. So at R equal to 1, efficiency is 0. Then it keeps on increasing with the value of R. Asymptotically, it should go to, I think it should go to 1. Okay. For R is equal to infinity. So similarly, if you increase the gamma, so obviously gamma will not change because it depends on the gas, but hypothetically, if the gamma is increased, again the efficiency for the same R will be higher. Typical values of R is nowadays it is around 20. Previously, when the new aircrafts like were developed 50 years, 60 years back, compressor pressure ratio used to be very less, around 5, 6 like this. Now it has increased to quite high values. Any questions on this part? So the other important, so there are two important things that we study, or two important output parameters that we study for any sort of industrial gas turbine. Okay, one is the efficiency of the turbine, and second is the work output, specific work output. Okay, per unit mass flow rate of air, per unit mass flow rate of working fluid, what is the work output from the turbine? What is the importance of specific work output? So efficiency, we know higher efficiency means we need less fuel, and less fuel is always means less cost, less operating cost. So for the same work output, for higher efficiency, we will need less amount of fuel. But what is the importance of specific work output? What will be the advantage of having larger specific work output? Say I need a turbine to generate 100 megawatt of power. Okay. So 100 megawatt is fixed. So I will design my turbine with 100 megawatt of power. So if I can increase the specific work output, what will be the design changes? What will be the advantage if I can increase the specific work output? The total power output is still 100 megawatt.
Sir, flow rate will reduce.
Flow rate will reduce. Good. So what is specific work output? Per unit flow rate, what is the work, right? So if per unit flow rate we can increase the work, then for a given amount of work requirement, we will be able to reduce the mass flow rate. What is the advantage of reducing the mass flow rate? Everything will scale down in size, right? Starting from the turbine size, compressor size, entire thing will scale down for lower flow rate. And then the expensive parts like the turbine blades are very expensive. One of the most costliest say part of the entire gas turbine are the turbine blades. They need to be manufactured very carefully. Single crystals are very expensive to make. Okay, so and the super alloys are also quite like very advanced technology. So all this will be sizes will be reduced, so cost will get reduced. And this is more important even for later on we will see for jet engines where you need less weight. Okay, for industrial turbines, okay, weight is not an important issue. Cost is still an important issue. So you want to reduce the overall cost, installation cost. So still it is better. So obviously it is better to have higher specific work output. Okay. So let us see how the specific work output varies. So for studying specific work output, we will define a parameter which is known as non-dimensional specific work output. We could have studied net specific work output directly, but by non-dimensionalizing it, we can actually plot the graphs and plots in or analyze analyze the work output in a better way in terms of parameters like pressure ratio, temperature ratio. I will show what is temperature ratio later on, and gamma values. So it is easier to relate to them once we non-dimensionalize it. So it is non-dimensionalized by dividing the work output by CPT1. Okay, inlet enthalpy CPT1. So what is the net work output? Net work output is CPT3 minus T4, turbine work output, minus the work input that is required for the compressor, CPT2 minus T1, divided by CPT1. So remember that for gas turbines, unlike steam turbines, the compression process takes a lot of work. Okay, it can take up to 50% of work also. So in real life scenario. So what is the reason for this? Why in steam turbines we need like a thermal power plant, steam power plants, we can we need very less amount of work input for increasing the pressure for, but here we need very large amount of work
The
input.
specific volume in case of water is very high, very small.
Yes, correct. So for water, specific volume is very small, and because the work input depends on integral of VdP. So if the specific volume is small, so dP for the same change in pressure, you will have much lower work input that is required. So pumps need much less work as compared to compressors. Compressors need very high amount of work. Okay, but here it is unavoidable because you have only gaseous product, right? You only have gas. In case of steam turbines cycle, we had water which can be condensed, and because it can be converted to liquid, we could increase the pressure in liquid state using very less amount of energy. But here we obviously we cannot change the phase, so we have to compress the working fluid in the gaseous state itself. That's why we need large amount of work is actually used up just for compressing the fluid. Anyway, so what I mean is that this term cannot be neglected at all. This is a very significant amount of the total work output that is generated by the turbine. Okay, so you cannot ignore the compressor work. If you have studied about steam turbines, you know this. In some cases we just can ignore the pump work input because it is so small. Okay, less than 1%. But here it is maybe 30, 40, 50% also. So anyway, so after you simplify this, divide by T1 and take T3 common. So T3 by T1, 1 minus T4 by T3. And for the second part, we will just keep it like T2 by T1 minus 1. Okay. So another important parameter. So one important parameter we have already discussed is the pressure ratio. Another important parameter is the temperature ratio. Inlet temperature is governed by the ambient conditions. Maximum temperature of turbine blades is fixed by the designer, engineer. Okay, depending on the material property, cooling, and manufacturing process. So this ratio of T3 by T1, maximum to minimum temperature, is known as temperature ratio. Okay, this is also a design input, similar to pressure ratio. So decided beforehand, okay, based on like what I have just said, turbine blades. Okay. So T3 by T1 is T, then 1 minus T4 by T3. What is T4 by T3? We have just studied here that T3 by T4 is R to the power gamma minus 1 by gamma. So T4 by T3 is 1 by R to the power gamma minus 1 by gamma. So this R to the power gamma minus 1 by gamma, we are going to encounter this term many times. So we can write this in a simple form as C. Okay. So because we will have it again and again, to denote it easily, we will write this as C. So C is R to the power gamma minus 1 by gamma. So this T4 by T3 is 1 by C. Okay, so 1 minus 1 by C minus T2 by T1 is R to the power gamma minus 1 by gamma. So this is C minus 1. Okay. So this is the expression. It cannot be simplified further. So this is the expression of net specific work output. So unlike efficiency, where efficiency only dependent on R, was only dependent on R and gamma. So obviously we are thinking that gamma is not changing. So it was only dependent on R. In this case, work output, specific work output or net specific work output in non-dimensional form also is both dependent on both R as well as temperature ratio T. Okay. So for the same R, if the temperature ratio changes, then we will have more specific work output, but the efficiency will not increase. Okay. Efficiency is independent of the temperature ratio. It only depends on the pressure ratio. So this net specific work output looks like this typically. If we plot with R at smaller values of T, it will look like this and it will go down to 0 after some time. So there is an optimum point. Okay. We will discuss why this optimum point is there, but it increases and again decreases. So for T equal to 3 also it will go down, but after certain, like at a large value of R. Then for T equal to 4. So it increases with T. With more temperature, you will get more work output. But there's an optimum R for each value of T. There is a different optimum R at which the work output is maximum. Okay. And you can find out at what value it goes to 0. And we will also find out the optimum. Optimum we'll find out in the next class, but at what value it goes to 0, you can easily find out if you equate this to 0, right? T1 minus 1 by C minus C minus 1 equal to 0. So for T equal to 2, if I take T equal to 2, By solving this equation, we get C equal to 2. Okay. So if C is equal to 2, then for T equal to 2, the work output will be 0. C equal to 2 means R to the power gamma minus 1 by gamma is equal to 2, which gives us a value of R equal to 11.31. So at a pressure ratio of 11.31, after that we will not get any work output. Okay. So obviously we do not use this type of small temperature ratios nowadays, but you can see that if the temperature ratio was small, like in old days, because the turbines could not sustain high temperature, we could not use very large pressures. Okay. So optimum pressure may be around 5 or something pressure ratio. Nowadays, for industrial turbines, we use P equal to 3 to 4, and for jet engines, we can go up to 5 to 6. Okay, temperature ratio. There are a couple of reasons. One is that jet engines do not constantly work at peak load. Okay, peak load is only used for takeoff and landing. Okay, not during cruise altitude. Industrial gas turbines will run at peak load most of the time. Second is that so as a result, the turbine blades can be designed with a higher temperature limit. And second is that the ambient temperature that the jet engines typically face will be lower for most of the time. Okay, because of high altitude for most of the time. So if the inlet temperature is low, even for high T value, the maximum temperature is still not very high, because this gives the temperature ratio, right? So if the inlet temperature is 220 Kelvin, for T equal to 5, you have 1100 Kelvin maximum temperature. But if the inlet temperature is 300 Kelvin, for T equal to 4 itself, you get 1200 Kelvin. Okay. So as a result, industrial turbines have low T and jet engines have a higher value of T. Nowadays, these are the typical values. Previously, this used to be much less. And these are increasing with time because we can develop better and better materials, better and better cooling techniques, and better manufacturing techniques for turbine blades. Okay. So for other cases also, it can be calculated. Okay. So this is how the two parameters varies, work input and efficiency. Let us take a look at an actual plot, how it looks like. Okay. We can easily write a code and see these things. Okay, we will do even for complex cycles like real cycles. We can compare different cycles by writing a small code. So I will show you for one or two cases. Means I will show you for all the cases, but maybe I will give you some assignments for the jet engines part. Write some codes. So actually, I have plotted here all the different cycles. At this point, we have not studied all the cycles, so you can ignore the other cases. But anyway. So this is how the efficiency varies with increasing R. You can see that around R equal to 30, which is like a practical limit. Theoretical efficiency is slightly higher than 60%. Okay. Obviously, in real life, there will be a lot of losses and the efficiency will come down to around 40% or even less. But theoretically, ideal cycle will have an efficiency around 60% maximum efficiency if everything was ideal. Okay. So we will also see the work output. So these graphs you can ignore for now. Okay, this we will study later. So you can ignore those graphs. Focus on this one. So this is for T equal to 2, the net specific, the non-dimensional net specific work output. Okay, it starts from 0 at R equal to 1, and you can see that it goes to 0 sometime after value of 10. So we have already calculated that value is 11.31. So we see that our graphs also concur with that, means it is showing similar result. So for this is for T equal to 3. Okay. So again, you can see that there is an optimum point where the work output is maximum. But this optimum is different from this. It is slightly at a higher pressure ratio. This is for T equal to 4. This x-axis obviously is the R, and this is the net specific work output in non-dimensional form. This is for T equal to 4, T equal to 5, T equal to 6. Okay. So all these cases have an optimum point. It is a very flat curve for T equal to 6, but still it has an optimum point at a high pressure ratio, okay, much higher than the other cases. So this is how the net specific work output looks like. We will later compare to other cases. We will see that with more additional components or changes, we can increase this significantly, but that is for later classes. So let us stop here and we will continue this discussion tomorrow in our next class. Any questions?